Welcome to the lecture series on numerical methods. Today's lecture will go for numerical differentiation. In the numerical differentiation, we will discuss about various interpolating polynomials, and based on this polynomial differentiation, we can just evaluate this functional derivatives. This means that if we are just approximating a function with a polynomial, that the derivative of this function can be written as the derivative of the polynomial also. So, that is why here first we will just go for an introduction section, that how we can just approximate a function with a polynomial. Then we will just start this differentiation by interpolation formula, first for finite difference formulas, then we will just go for undetermined coefficient, and in the last phase we will just discuss about this unequal interval. So, in this section, if you will just see that the estimation of a value of a derivative based on certain known functional values, always certain values has been given, and at that points usually we are just evaluating the derivatives. Sometimes if the exact function is not known to us, then we can just approximate this function by a polynomial, and we can just evaluate the derivative for the polynomial, and then we can just say that this derivative of this function can be represented in this form there. So, several methods are available to find the derivatives of the function by using given set of tabular datas. Like if you will have this set of tabular datas like x0, y0, x1, y1 to xn, yn, even if the function is not known to us, we can just evaluate this derivative of that function at certain points. So, here we will discuss both these methods based on both equal and unequal spaced data points. Since already in the last lectures we have discussed that some of these interpolation polynomials that deals with this equal spaced points, some interpolation polynomials that are based on both these equal spaced points and unequal spaced points, and we have also discussed what are the drawbacks or what are these advantages of different interpolation formulas. So, the methodology for computing the derivatives at a given point is rather simple, since if you will just find this derivatives like dy by dx equals to f of xy. So, various methods are available to evaluate this first order derivatives, but if the function is exactly known to you, it is easy to evaluate. So, we have already discussed how we can just approximate the function with a polynomial in the last classes. In order to find this derivative of this function here, we can just differentiate this approximated polynomial p n x with this function f of x here. This means that if we are just the tabulated points like x0, y0, x1, y1 up to xn, yn here, where only that tabular values are known to us, but the function is not known to us, then we can just formulate a polynomial by considering all these tabular points here, and from that polynomial we can just find the derivative for the function. And at certain points, if it is required to evaluate these derivatives, then at that point exactly we can just put in the polynomial derivatives there, and we can just evaluate these derivatives for that function at that point. If you will just see this graph here, that is y equals to f of x is the curve we have plotted, and this curve is approximated by a polynomial y equals to px here. And if this is approximated, if you will just visualize a point A in this graph here, and if you will just plot the tangents at that points like AF and AP, we can find that these tangents are completely different. Then we can just say that sometimes this polynomial's differentiation is completely differ from this approximated functional derivatives. So, but if you will just use different techniques to find this numerical differentiations by sufficiently close to these tabular points, then we can just obtain this derivative for the function is equals to the derivative for the polynomials. This means that we have to do this domain discretization in a sufficiently close form that these tangents at different points for both these functions it should be equal. Then we can just say that this derivative for the function and the derivative for this polynomial are equal. So, first in this discussion we will just consider this equispaced points. Whenever the points or the tabular points are equally spaced, how we can use this differentiation there. Then we will just go for finite difference operators, then we will just go for undetermined coefficients. Suppose we will have this given set of data values of f of x like x0, x1 up to xn. In general approach, we can just derive this numerical differentiation method first to obtain an interpolating polynomial there. Then differentiate this polynomial. Suppose r times, if you will just differentiate this polynomial, we can just write this polynomial as p n r x suppose. This means that first we are just approximating, if you will just see f of x is approximating with a polynomial of order p n x here. This means f of x is approximated with a polynomial p of x of degree n. Then we can just write this nth order difference or this differentiation with respect to p n x with respect to r in the order of r as can be written as p n r x here. So then at a particular point we can just write this polynomial differentiation of order r as p n r of x k, where this differentiation is evaluated at the point x equals to x k of order r there. It may be noted that p n x and f of x may be sometimes they have the same values at the nodal points, but the derivatives are different, that I have already shown in the graph. First we will just go for this equispaced points, and the first equispaced differentiation interpolation we will just do, this differentiation with the interpolation we will just carry out here is Newton's forward interpolating polynomial. So basically this interpolating polynomial for Newton's forward difference formula is expressed in the form of like y for any point xp, or usually you are just writing y of x or y at xp, or we are just writing yp. This can be written as in the form of like y0 plus p delta of y0 p into p minus 1 by factorial 2 del square of y0 plus up to like p into p minus 1 up to p minus of n minus 1 divided by n factorial del to the power n of y0 here. So if we want to differentiate this one, first we have to consider this xp point as x0 plus ph here, and especially this xp is nothing but the undetermined point or the point where we want to find this interpolation polynomial or the formula. So at that point, especially if we want to differentiate, we can just write dx equals to h dp here. Or we can just write dp by dx that as 1 by h here. Either ways you can just define this first order differentiation here. So if you will just write this differentiation for this polynomial here, we can just write dy by dx, that is the first differentiation of y with respect to x here. So we can just write dy by dp into dp by dx here, and especially it can be written as 1 by h, since all of these points or this function whatever it is just expressed here, that is a variable of p. So that is why it is easy to differentiate this function with respect to p here. So that is why we can just write this one as a d by dp of y0 plus p delta of y0 plus all these points here. And if you will just differentiate that one, so directly we can just write this one as 1 by h. First point if you will just differentiate, that will just give you 0 here. Second point we will just get as a del y0 here. Third point if you will just differentiate here, that is in the form of like p square minus p by 2 factorial here. So it can be expressed as 2p minus 1 by 2 del square of y0 here. So likewise all of these other points you can just differentiate there. So in a complete form if you will just write this one, then dy by dx can be written in the form, dy by dx can be written as 1 by h. So, first point we are just writing here del y 0 plus 2p minus 1 by 2 del square of y 0 plus 3p square minus 6p plus 2 by 6 del q of y 0 plus likewise. Similarly, if you will just go for this differentiation of second order, we can just write the second order derivative as d square y by dx square. This is nothing but we can just write d by dx of 1 by h dp by dx here. So, once more if you will just differentiate this one, we can just write this one as 1 by h square d square p by dx square here. So, if you will just go for this second order differentiation of this formula here, once more if you will just differentiate this one, we can just write this one as d square y by dx square, this equals to 1 by h square. So, since once more we are just differentiating this one with respect to p here, so this term will just give you 0 here. Second term, if you will just differentiate this one with respect to p here, so 2 by 2 this is a 1 here, so del square of y 0 is the first term here. Then second one if you will just see here, so 6p minus 6 divided by 6 del q of y 0 plus all other terms, it will be carried out in the same fashion here. So, this formula especially can be used to compute the first and second derivatives respectively near the upper end of the table. This means that at the beginning of the table, if the data is suppose asked to find, then we can just use this formula at that point. Since already in the previous classes we have discussed already that Newton's forward difference formula, especially it is used if the tabular value is asked at the upper end of the table or the beginning of the table there. So, if suppose this tabular point is asked to compute this derivative exactly at suppose the nodal points, this means that if it is asked to compute at x equals to x0 or x equals to x1, especially we can just find that at that point exactly p equals to 0. So, then we can just reduce these formulas as suppose it is asked to obtain the derivative at x equals to x0 suppose. Then we can just say that p equals to 0 at that point, and we can just write dy by dx at x equals to x0 as 1 by h delta of y0. Since p equals to 0 here, we can just write this one as minus half delta square of y0 plus, so 2 by 6 here. So, that is why you can just write 1 by 3 delta q of y0. So, all other points it will be considered in that form only. Similarly, if it is asked to compute this d square y by dx square at x equals to x0, then this formula can be written in the form like 1 by h square. If you just see here, this means that we are just obtaining p equals to 0 here. So, that is why this can be written as a del square of y0 minus del q of y0. So, all other points would can be considered in the same fashion there. So, it can be written in the form of like 1 by h square del square of y0 minus del q of y0 plus 11 by 12 del fourth of y0 minus, so all other terms. So, first for this type of differentiation we can just consider one example here. So, if you will just consider this example that all the points are equispaced here. So, if you will just take this tabular points like x, y as 2.00, 2.20, 2.40, 2.60, 2.80 and 3.00 suppose, and its functional values are expressed as like 0.6932 and 0.7885, 0.9555 then 1.0296, sorry, one more point I have missed here. Just if I will just write this point as 0.7885 at 2.40, it is 0.8755, then at 2.60 if the value is 0.9555, and at 2.80 suppose the value is 1.0296, and at 3.0 suppose the value is 1.0986 suppose. So, first differentiation easily we can just obtain, since in the last lectures we have already explained that one. So, we will just consider the difference of these two values here. So, first differentiation, we can just take the differences like 0.7885 minus 0.6932. So, it can be written in the form of like 0.0953. This is the difference of these two values here. Similarly, if you will just take the second difference values here like 0.0870, if you will just take the difference of these two values here, so that can be written in the form of 0.0800. The difference of these two values, it can be written in the form of 0.0741. The difference of these two values, it can be written in the form of like 0.0690. Similarly, for the second difference, we can just consider the difference of these two values here, that will come as like minus 0.0083. Difference of these two values, we can just write this as a minus 0.0070 here. So, third point we can just write minus of 0.0059, and the last one we can just write minus of 0.0051 here. For third difference, if you will just see, we can just take the difference of these two here, and that can be written in the form of like 0.0013 here, and if you will just take the difference of these two here, that can be written in the form of like 0.0011. If you will just take the difference of these two here, that can be written in the form of 0.008. And in the fourth difference, if you will just take the difference of these two here, that can be represented as a minus 0.0002, and last difference, this one also minus 0.0003 here. So, if you just put all these coefficients in the Newton's forward difference formula within differentiation up to third differences here. So, fourth difference, if you can just see that values are very small here. So, that is why you can just consider these differences up to third differences here. Since the question is asked that using this following data, find y dash and y double dash at 2.00. This means that at x equals to x0 there, using up to third differences only. So, if you just use here up to third differences, we can just write this formula dy by dx, that in the form of like first term, if you just write here del y0, first one is 1 by h here, minus half del square of y0 plus 1 by 3 del q of y0 here. And since it is asked to evaluate up to third differences, we can just write these terms up to third differences here only. For the second order differentiation, we can just write d square y by dx square, this equals to 1 by h square. So, first differentiation term here we can just get it as del square of y0 plus del q of y0 here. Sorry, this one is minus here. So, if you just put these tabular values for x0 equals to like 2.0 here, then we can just obtain this first difference term as like x0 equals to 2.00, so h equals to 0.20 also. So that is why y dash at 2.00, it can be written as 1 by 0.2 into the first differentiation value, that is 0.0953 minus half into minus 0.0083 plus 1 by 3 into 0.0013, this equals to 0.4994 here. And if you will just use for the second order differentiation here, then we can just find this as 1 by h square, that is 1 by 0.2 whole square into del square of y0, that is nothing but minus 0.0083 minus del q of y0, that is minus 0.0013 here. So the total value is a minus 0.24 here. So next we will just go for Newton's backward interpolating polynomial. In the Newton's backward difference interpolation formula, especially this formula is written in the form like y of x or y of xp or especially y of p. It can be represented in the form of like y0 plus p nabla of y0 plus p into p plus 1 by factorial 2 nabla square y0 plus all other terms are there. So if you will just write here p, then p can be represented in the form of p equals to x minus x0 by h here, or x can be written in the form of x equals to x0 plus ph here. And if you will just define here dp by dx here, so dp by dx, especially if you will just differentiate both the sides here, this can be represented in the form of 1 by h here. And if we will just go for this differentiation here for this function y of x here, then we can just write dy by dx as dy by dp, since y is a function of p here, this into dp by dx here, and especially it can be written in the form of 1 by h dy by dp here. So then if you will just go for like a second order differentiation here, then this can be written as like d square y by dx square, this equals to d by dx of dy by dx. If you will just see here, that is dy by dx can be replaced by 1 by h dy by dp, and then we can just write this one as 1 by h square d square y by dp square here. And if we can just put this formula, or if we will just write this one in the form of like y of x there, then we can just represent this one as dy by dx as 1 by h d by dp of the complete formulation, that is y0 plus p nabla of y0 plus p into p plus 1 by factorial 2 nabla square y0 plus all other terms are there. And if you will just differentiate this one, then we can just get this one as 1 by h. So first differentiation, this will just give you del y0, since y0 is a constant, that will just give you 0 value here. So then next one we can just write that as 2p plus 1 by 2 factorial del square of y0 plus the third order term we can just differentiate, we can just write there. And similarly, if you will just go for the second order differentiation here, then we can just write d square y by dx square as 1 by h square. And one more differentiation for these functions, if you will just write out here, then the first value, since del y0 is a constant here, then we can just write the second one as del square of y0 here, since the differentiation if you will just take here 2p means this is 2 by 2, it will just cancel it out. So first term it will be like del square of y0 here, plus if you will just see here, then immediate next term it can be just represented as p plus 1 into nabla q of y0 plus all other terms are there. and especially if we want to find this formula at the upper end of the table, since usually I have explained to you in the previous lectures that this backward difference formula, it is used at the end of the table. So that is why if it is asked to find the value near the upper end of the table or at the lower end of the table, then we can just use Newton's forward difference formula and the backward difference formula there. Suppose if you will just use this tabular point at x equals to x0, suppose where p equals to 0, this means that we are just shifting this point to the lower end of the table, and at that point only we are just using these p values. So that is why if you will just put at the lower end of the table x0, then upper points it will be represented in the form of like x of minus 1, x of minus 2 up to x of minus n there. And if you will just put, this means that if x equals to x0 exactly, then we can just put here p equals to 0. So that is why your formula can be reduced in the form of like dy by dx, it can be represented as 1 by h nabla of y0 plus, since p equals to 0 here, then we can just write this one as 1 by 2 nabla square of y0 plus rest of the terms, it can be represented from the formulation there itself. Similarly, if you will just put this p equals to 0 in the d square y by dx square here, then we can just obtain this value d square y by dx square at exactly x equals to x0 at the lower end of the table, and at that point we can just say that 1 by h square. So first value it will be nabla square y0 plus, if p equals to 0 here, then this will just give you nabla cube of y0 plus all other terms are there, and immediate next term, it if you will just write this one, then it can just give you 11 by 12 del to the power 4 of y0 here. And if you will just go for the set of data points, like the data points is given like 1.00, 1.25, 1.50, 1.75, 2.00, 2.25, and their corresponding y values are like 2.7183, 3.4903, 4.4817, 5.7546, 7.3891, 9.4877. And if you will just use this backward difference formula, so in the backward difference formula, if you will just see, first we are just taking this first difference, that is nothing but the difference of first two values, but we have to consider these values, like if we can just write x0 at the end of the table here, then our tabular values will be followed like from the bottom to the up of the table. So that is why we can just consider these tabular values that in the form of, so if you will just use these tabular values that in the form of like 1.00 as 2.71 and take the differences like 3.4903 minus 2.7183, then it can just provide the values as 0.7720 here. If we will take the difference 4.4817 minus 3.4903, then it can just provide us the value 0.9914. So likewise the differences we can just calculate, and if you will just use in the differentiation formula here, since the question is asked to find y dash and y double dash at x equals to 2.25, since it is at the end of the table, using up to third differences. So up to third difference formulas we will just consider. Up to third differences, this formula can be written in the form of like dy by dx, that is 1 by h nabla of y0 plus half nabla square of y0 plus 1 by 3 nabla cube of y0 here. And similarly for second order differentiation, we can just write these forms in the Newton's backward difference formula up to third order terms as 1 by h square nabla square of y0 plus p plus 1 nabla cube of y0. And if you will just put here h equals to 0.25 and x0 equals to 2.25 here, then we can just obtain this derivative as y dash at 2.25, that s 1 by 0.25. If you will just see this tabular values, del y 0, it is just giving you 2.0986 plus half into the second value, that is nabla square of y 0, that is coming as 0.4641, and last value 1 by 3, that is nabla q of y 0, that is coming as 0.1025. So, if you just evaluate this values, that will just come as 9.4593. Similarly, we can just obtain this derivative for second order, that is at 2.25 point also, and it can be written as like 1 by h square. So, that is why we can just write 1 by 0.25 whole square into your nabla square of y 0, that is 0.4641 plus 0.1025, that is 9.0656 here. So, maybe next class we will just continue about this differentiation using a Lagrange interpolating polynomial, that is for both for equispaced points and unequispaced points. Thank you for listening this lecture.